Hello geometry students, welcome to the chapter 6 review. Hopefully you've tried as many of these problems as you could do on your own already. We're going to look at each one of them and just use this as a tool to help you on the ones you need to. Fast forward as needed, pause as needed, go back as needed to help you understand and be ready for the test coming up very soon. So let's check it out. I've already got them all copied and pasted into here. This one I had to copy. I took a picture of my book, and so you might see some kind of wavy looking text because I couldn't get it perfectly straight, but it should all be legible. So number 1, draw a figure that fits the description. So a regular pentagon. I'm going to cheat a little bit here, and I'm going to use my pentagon tool. I'm sorry, you don't have one of those, but I will talk about this. So a regular pentagon, this would not be a regular pentagon because not all the angles and sides would be the same, but I'm going to make it as best I can so that it is a regular pentagon, so that everything does look the same. So I'd say that's pretty close here. I'm not being so picky as to get out a measuring implement and measure each side, but I'm saying what is true about a regular pentagon. All the angles and all the sides are the same. It's both equilateral and equiangular. So I can put this in there, and then that assures me that that would be a regular pentagon. Right? A concave octagon. This one, I won't cheat on this one. I will just draw an octagon. So it has 8 sides right here. This means 8 sides. And then this concave part, it kind of caves in. There's at least one part where it caves in. Think of concave like that. And so I could do 1, 2, 3, 4, and then I'll make this my caving in part. 5, 6, 7, and 8. That would be an octagon right there. Yours could look a lot different than that. It could cave in more than once, but at least it has to have one part caving in. The technical definition of concave would be any segment you draw in here, no part of that segment could be in the exterior of the shape. Here, if I drew a segment connecting these 2 points right here and here, right here to here would be on the exterior of the shape, therefore it's concave. But that's the easy way to think of it is just think, does it cave in anywhere? If it does, then that would be a concave octagon here in this case because it has 8 sides. Let's move on to numbers 3, 4, and 5. So all of these, we're finding the value of x. These are all quadrilaterals, therefore they should all be adding up to 360. So it looks like should be some pretty straightforward problems here. So 67 plus 115 plus 63 plus x should equal 360. Another way to think of that would be if I'm thinking of this all together, you could write it as x would be 360 minus these 3 added together. So if you wanted to do that first, if you wanted to figure out what this was first and then subtract that, you could do it like that, or you could do it like this. I'll get out my calculator on this one just to make this a little faster. So 360 minus 67. I'm also subtracting 115. I'm also subtracting 63 from 360. So that would be 115 overall. If you wanted to do 67 plus 115 plus 63 first, and then subtract that from 360, that's okay too. And so any way you do it though, you should get x is 115. So this one, x would be 115. If you left out the degrees here, I think that would be okay because it's x is the number in front of the degree symbol. So I'm just going to say 115 right there. Number 4, this and this means those are both 90 and 90 degrees. Boxes in the corner, so I have 90 plus 90 plus 5x plus 3x, x, there we go, plus 3x would equal 360. I'll combine like terms on this one and do it more like a traditional algebra problem here. This would be 360, subtract your 180, 8x equals 180, divide by 8, and this one turns out not to be a nice whole number. It would be 22.5. You just do 180 and divide it by 80 in a calculator. You could also think of it as divided by 8. Sorry. You'd also think of it as 180 divided by 8, you could reduce that until you couldn't reduce anymore, and then find out, oh, it's still a fraction, so you could write it as a decimal. Number 5, though, just do that here to separate this from these two. So number 5, we have this, 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 and this. They're all adding, same sort of thing. They're all adding to 360. It's a quadrilateral. So 75 plus, I'll do 75 plus 90 together, and then 9x and 6x, I'll put those two together, would be 360. This would be these two added together. That looks like it's going to be 165. These two put together, combining like terms, that would be 15x would equal 360. Subtract 165, and then divide by 15. This is going to be 195, it looks like. Yep. Divide by 15. That means x would equal, let's take the calculator out and figure that out. So 195 divided by 15, x equals 13. And so if I get my final answer, I want to box those in, sorry. There we go. So let's check my answers. It looks like yep, yep, and yep. So ready to move on and check out numbers 6, 7, and 8 here. So using parallelogram, it could be important. We know some properties about parallelograms. So DEFG at the right. If DH is 9.5, so it's saying right here, I'll use red for that. DH is 9.5. What is FH and DF? Alright, so FH, we know diagonals bisect each other in a parallelogram. So I know that this would be the same as this. That would mean, for number 6, that FH would equal 9.5 as well. And then DF would be the whole distance from here to here. So DF, that must equal 9.5 times 2, or 9.5 plus 9.5. Either way you could think of it. That's going to be 19 for DF. So DF would be 19. Number 7, I will get rid of this stuff. I'm going to keep drawing on this picture for each one separately. So if G to E is 65, G, D, E. That's starting at G, going to D, and then going right there to E. They're saying that whole angle is 65 degrees. Find the measure of EFG. So find this one, and find DEF. So find this one. Here's D to E to F. We know opposite angles are congruent, so this one's the same as this one. And then we know these two are supposed to add to 180. In a parallelogram, these two are also supposed to add to 180. The consecutive interior angles are supposed to be supplementary. And so we have that angle right there, EFG. Measure of angle EFG is going to be the same as G to E, so it's 65 degrees. And the measure of angle DEF is supposed to add to 180 with the other one, so it should be 115. So 115 coming from 180 minus 65. So that's our final answers for both of those ones. And then number 8. There we go. Number 8, find the perimeter of DEFG. Perimeter just means you add up all the sides of the shape in question. And so this one, 12 and 10. But they don't have numbers here and here. However, we know that a parallelogram, this is a parallelogram, that didn't change, it's the directions for all of these. This is going to be the same as this, and this one's going to be the same as this one. So I know this is 12, and I know this is 10. So all I need to do is add up those four numbers. So 12 plus 10 plus 12 plus 10. You could do 12 times 2 plus 10 times 2. That would give you the same thing. This is going to be 22 plus another 22 is 44 for that one. And so we're good to go on those three. Let's move on to 9, 10, 11, 12. Is it a parallelogram? And so this is kind of the reverse of what we just did over here. Here we knew it was a parallelogram and could say some properties about it. And over here we're going to say that the properties, certain properties are true. Does that mean it's a parallelogram? So let's draw a shape here. I'm going to draw one that's a nice looking parallelogram with the words already, the letters already labels. Excuse me, I'm having a little brain fart here. So the labels already put in there, and then I will kind of do each one and clear the picture each time. Alright, so there we are. This is looking like a parallelogram, and that's on purpose, but we can't assume that it is unless we have certain properties about it holding true. So let's see, number 9, is that enough? If PQ was equal to QR, this equals this, and RS equals SP, if this one equals this one, is that enough to prove it's a parallelogram? I would say no, because that's what's going to be true about a kite. And kites have two pairs of consecutive congruent sides. So on this one, we don't have stuff about the opposite side, so I would say no. And it says to explain, so I would say no and then give an explanation. And I could say something like this: we aren't told opposite sides are equal. And that's what we need for a parallelogram. If we're going to say things are equal, and that's all we're given, that's not enough. So this would be a kite. So if you wanted to know that, that could be true, or that would make it for sure a kite. This is a kite, though. Okay, so let's do number 10. I will erase the markings here, so think back to this picture, and let's label what's given to us. So SPQ is congruent to QSR. Notice when I drew PQRS, I had put the letters in order. That's got to be the case. The way they're written, the vertices have to go in order. And so SPQ, that'd be this right here, SPQ, congruent to QRS, this one right here. And PQR, so here's P to Q to R, that's this angle right here. Is that congruent? It is congruent to RSP. And so they're saying these two are congruent. So if you have a picture like that, is that enough? Yes, it is. That's because opposite angles are congruent is enough to prove something is a parallelogram. So yes, because opposite angles are congruent. So there's number 10. Now number 11. Start afresh, start anew. We're saying this time that PS is congruent to RQ. PS congruent to RQ, and PQ is congruent to RS. Okay, so is that enough? Yes. Now we have number 9. It wasn't enough. We had consecutive, but now we have opposite sides. So this one, yes. And why? Because opposite sides are congruent. Sides, there we go. And number 12. So let's start afresh one more time. So what this one's saying is that PSR is this one plus SRQ plus this one, saying that these add to 180. So add to 180 degrees. And also that PSR is congruent, so PSR is this one, is congruent to RQP is congruent to this one. So if these two are the same, and these two add to 180, these two must also add to 180 based on the fact that this is the same as this. So whatever this is, if you called this, if you went and generalized it like this, if you said this was X degrees, this would also be X degrees, making this, if it's adding to 180, this one would have to be 180 minus X degrees. Therefore, these two are supplementary, these two are supplementary, and so this one's another yes, because if you pick an angle and you find one, the angle, it's supplementary to both of its consecutive angles, then you have a parallelogram. So this one, yes, because consecutive angles are supplementary. And so that'll do it for this set, for 9 through 12. Let's check out the next. And hold on there, hold the phone a second. I went too fast for number 11. So hopefully, if you watch number 11, you caught my mistake. Look here. this went too fast. That means parallel right there. And so this one's actually a little more complex than what I was thinking there earlier. So PS is congruent to RQ. So PS is congruent to RQ for number 11. This is number 11 now. So this one, we'll have to make some changes here. PS congruent to RQ, and that PQ is parallel to RS. So this is parallel to this. So is this enough to prove this? So if you wanted to, you could do something like this. Let's see what we got here. Do I want to do it that way? I'm going to draw in an auxiliary line here, and then with that you could say some different things here. Let's see what I could say from there. Okay, so I got it now the way I want to prove this. This one's not quite as straightforward, but it's actually still possible to prove that it's going to work out here. So let's see what we got. We have, I had it, now I lost it. Just a second. I know I can say this at least. I'm trying to prove that these two triangles are congruent. Okay, so let's go back one step there. I'm going to draw in both diagonals on this one. So I'm going to draw that one and that one. And so if that is done, let's see. We have parallel lines here. That would mean this is congruent to this. It would also mean that this is congruent to this. Those are alternate interior angles with respect to these two transversals. And so if I called this T, what else could I say here? We know is it a parallelogram? They do. Give me another minute. I'm going to think about this a little bit more. Okay, so I'm looking at the book. I'm assuming that they're getting this right. Once in a while, I think the book makes a mistake, though. And so the more I look at this, I was saying yes at first, but that's because that's what the book says. It says yes. My copy of the teacher's edition here says yes, that is possible, but I have to disagree. Because PS is congruent to RQ. So if PS is congruent to RQ like it is here, and PQ is parallel to RS, I could draw a picture, something where that is the case, and this is still parallel to this. This is PQ, R and S, and these two are congruent, but that is not a parallelogram. This is clearly an isosceles trapezoid. So this one, disagree with the book. This one is going to be a no, because what is it going to be instead, or actually? So this one's a no, because it could be an isosceles trapezoid. So I'm going to have to go back in the video and put a little annotation there. If you're watching number 11, hopefully you're watching a little bit longer. Originally, it would have been yes if this was congruent and this was congruent, but I misread that. That says parallel, not congruent. And so it's possible to have a picture, to have something where that's not the case. So this is you could call this a counterexample for number 11. Okay, let's move on and look now at numbers 13, 14, and 15. So 13, 14, 15 list each special quadrilateral for which the statement is always true. Consider parallelograms, rectangles, rhombuses, and squares. So we're only going to consider these four things. Diagonals are perpendicular. Okay, so why don't I'll pause the video here and I'll draw a really good example of each one of these. So I'll draw a really good example of a parallelogram, rectangle, rhombus, and square. Okay, so that'll be very helpful as we think about these problems. Number 13, the diagonals are perpendicular. So if you take any old parallelogram, I'll just draw some general parallelogram. Is it true that the diagonals are always going to be perpendicular? If you tell me that this is 90 and this is 90, I'm going to tell you, get out your protractor, think again. This, if you put it right here, I drew these pretty well, and so is that a 90-degree angle right there? 90 would be from here going up this way. Clearly, that's not always going to be the case. And so you could do the same sort of thing with rectangles and see that they're not always going to be perpendicular. It's not always going to be 90, but if you draw on the diagonals for a rhombus, this will always be 90. And if you draw on the diagonals for a square is just a special type of rhombus, that's also going to be 90. So is this going to work? If you remember your properties, you wouldn't necessarily have to draw these out, but drawing them out, actually drawing in all the pictures, makes it easy to see. I think that diagonals are always perpendicular in a rhombus and a rectangle, or in a square, sorry. Rhombus and a square. So I'll erase this. I'm going to use Mega Eraser, there we go. And do number 14 now. So opposite sides are parallel. So parallelograms, yes, opposite sides are parallel. And then rectangles, rhombuses, and squares are just special types of parallelograms. So yes, this is going to be parallel to this. This is going to be parallel here and here. And this is going to be parallel here and here too. So we've got all of them in that case. Oops. So this one should be all four. Parallelogram, you can use the little symbol for that if you want. Parallelogram, rectangle, rhombus, and square, Number 15 is equilateral. Equilateral just meaning that all the sides are the same length. And that one should be really easy to do, because the only ones where all the sides have to be the same length, that would be a rhombus and a square. And so this one, the rectangles don't have to be that way, and this is saying always true, remember. So parallelograms don't have to be that way either. So you would say just rhombus and square on this one. And that'll do it. Let me get rid of this. In numbers 16, 17, and 18 now. Use a diagram of isosceles trapezoid A, B, C, D. So there's a diagram in your book. Let me recreate that diagram right here. I forgot to copy that picture over to here. Okay, so here's the diagram, and it says this is A, B, C, and D in your book. And it also gives us that this is the same as this, and this is the same as this. Anything else? Yep, one more thing. So isosceles trapezoid, you have to have something like that too, so it tells us in the book that that's the same as that. So let's see what we got here. I'll use green for this one for the things that I might be erasing later. So AB is 6 right here. CD is 16. We're going to say that's true. We're trying to find the length of the mid segment, so the one that would connect the midpoints. So what's the length of that mid segment going to be? And so I'm going to undo the green stuff there, but hopefully it's easy to tell. If you remember about trapezoids, it's going to be the average of the two bases. And so this part's parallel to this part. Since it's a trapezoid, the average of these two numbers, you take those two, add them up, and divide by 2. Or you can think of that as being the same thing as multiplying by 1/2. So 16 would be half of 6 plus 16, which would be half of 22, which would be 11. So number 16, 11 is the answer. Number 17, measure of DAB. That's D to A to B, so that's this angle right here is 112 degrees. Find the measures of the other angles of A, B, C, D. So that one I'll leave it up there for a second. I know that this is the same as this, so I could say that the measure of, I could call this A, B, C. I would want to use more than just B because there's extra marks coming out of that. So if I said B, you got to be more specific. You got to tell me if it's ABD, if it's ABC, or if it's DBC. So ABC would work for that one. That'd be 112 degrees. The measure of the other angles, we got ADC would be another possibility. We know since this side is parallel to this side, these two should add to 180. So we should say that that one would be 68. That is 180 minus 112. And the same thing is going to be true since that's congruent to that. Same thing is going to be true about DCB. You could also call it BCD. C's got to be in the middle though. So 68 degrees, that's the same thing there. So that should be it for number 17. And number 18, see what we have on this one. Get rid of that. There we go. And it says that explain how you could use congruent triangles to show that ACD is congruent to BDC. So let me draw in green those angles. ACD would be this angle right here, ACD right there. How could you show that that angle is congruent to BDC, B to D to C? So this angle right here. How is that possible? We know this is an isosceles trapezoid, so I know that this is going to be parallel to that. That may prove to be helpful. So let's see here. So here's my thought process right now. This is the first time I'm looking at these problems. I'm seeing that the ones in yellow I'm coloring in here. These two are the only two triangles that look like they might be congruent. It says use congruent triangles. And so I'm thinking that I might be able to prove this is congruent to this one over here. I already know that this side's congruent to this side. I know that this one's going to be congruent to, I'm trying to use my green here, this one's going to be congruent to this one. I should use 3 since I've used 1 and 2 already, by vertical angles. And what else could I say here? Do I know anything else is going to be true? This is the whole angle right there. So let me think about this a little bit longer. Yes, okay, so I said that that would be the only one that I saw, but correction, I stand corrected on that. Let me draw in a couple other congruent triangles, potentially congruent triangles in this picture. And I think you'll see what I mean after I draw them in. So I'll go with blue on this, and I'll do this. So here to here to here to here. That one could potentially be congruent to this one right here. Here to here to here. So I'm going to move those off to the side. That was triangle BAC, and this one is triangle DAB. So I'm going to try to prove that these are congruent here. So here's D, A, and B. Stick with blue for now. D, A, and B. I just copied that triangle right here and put it in the picture over here, a separate picture, to make it easier to think about. We know this is C, B, and A. We're told that this angle is congruent to this angle. We got the red mark here and the red mark here. We're also told that this is congruent to this. And I know that AB is the same thing as AB. AB is congruent to itself. And so this triangle right here is going to be congruent to this triangle right here by side, angle, side. And so let's put those thoughts down on paper. We'll use a paragraph form for this type of proof here. I can say something like this. We can prove triangle ADB is congruent to triangles A to D to B would be matching up in this triangle with B to C to A. So the triangle BCA by side, angle, side. Because I can say angle DAB is congruent to angle, so DAB is congruent to CBA, and that's given. What else? We've got AD is congruent to BC. That's also given in the original statement because it's an isosceles trapezoid. And we can say that AB is congruent to itself. AB is congruent to BA. I'm doing this in a slightly different way than the book is, it looks like, too. I just looked at the book and noticed they're doing what actually is a little easier way, because they saw this one and they saw this one. But the way I'm doing this, it should be fine, too. So ACD, yeah, this should work out just fine. So AB is congruent to itself by the reflexive property. So from there, what I'm trying to prove is that ACD is congruent. So ACD, this one right here, is congruent to BDC, right there. Okay, so if that's true, I can now say this. I can say that this angle here is going to be congruent to this angle over here. So just looking at these two triangles, this is going to be true by that CP-CTC property. So because I have this being true, because these two triangles are congruent, I can say something like this. Therefore, the measure of, no, I don't want to say measure. I want to say angle ADB is congruent. ADB here is congruent to BCA right there by corresponding parts of congruent triangles being congruent. CP, CTC. And so if that's the case, if this angle right here is equal to this angle right here, that means I can say this angle right here, and I'll use 3 in this one, would be congruent to this angle right here. And so if this angle is congruent to this angle, and this whole one right here is congruent to this whole one right here, if I subtracted this one from the big one, I'd be left with this one. So this is actually, I think it's just taking one more step than the way the book proves it. The way the book proved it was a little more straightforward, a little more direct. So I'm showing you an alternate way than what the book has. So I would say, you could say this from here. So therefore, I'll use another therefore. The measure of A, let's see how I said that at first. Measure of ACD, just a second. I can say this, the measure of ADC equals the measure of angle BCD, and I can also say the measure of ADB, which is what I had right here, the measure of ADB is equal to the measure of angle BCA. And these would both be by the definition of congruent angles. If they're congruent, they're equal in measure. So I could say the measure of angle BDC just reconsidering how I want to say this to try to make this as easy as possible to follow. So the measure of BDC, this angle right here, BDC, this angle right here, that green one that I originally drew in there. Measure of that angle is going to be this big one minus this one. So measure of BDC equals a measure of, that would be ADC minus the measure of BDC minus the measure of ADB so this would be ADC minus, so here's ADC minus ADB. So I'd say that would be true, as well as measure of angle. So the other green one here, this one right here, that would be ACD. So it's the opposite of what I had here. BDC was this one. ACD would be this one over here. Would be the big one. Measure of, over here was ADC. Over here it's going to be ACD. ACD minus this one, BCA. So if we look at this, we can, what we're doing here, I think I wrote one of these things down wrong, which was confusing me here. So BCA, that's this angle, BCA right here. That should be equal to ADB. So I wrote down the wrong thing right here. So let's erase that. ADB. Let me see if that looks good now. So ADB would be that one. And that's what I have here too. So ADB and BCA. That's better. And so I have the big angle minus the smaller one gives me this black one and this black one. What's left over? And so because that's true, and that would be true by this definition of congruent angles, and subtraction property. So we could say the subtraction property. Subtraction property. Because I'm taking this right here and this right here. They equal each other. This one equals this one. And so this is, I'll double underline this one. This is the double underlined part plus a single underlined part. And this is double underlined part minus a single underlined part. These things would be equal. And so we could finally say, based on that, I'm going to squeeze this in here. So I'll put a period there. So since this equals this and this equals this, and because these two equal each other, we could now say finally that the two angles are going to be congruent to one another. So we could say that angle ACD is going to be congruent to angle BDC. And that is a D. I would not give myself an A for that explanation. I was kind of messing that up a couple places here and there. And so I think the clearer, the more straightforward explanation is in your book, or in the teacher's edition. So you could check that out in my book if you'd like to. But this is another valid way to prove it. It's just a little more convoluted, a little more lengthy in terms of a proof. It didn't say you had to prove it necessarily, it just said explain, so it could be kind of a more rough proof, but this is a rough explanation of why this works. But you've got, in my book, you can check out a more straightforward explanation of why it works. But let's check out now 6.6 problems, these three. So what special type of quadrilateral is PQRS? Give the most specific name and justify your answer. And so just like that, I've got a grid on here. I'm going to move this off to the side. It's looking like my largest x values or y values positively are going to be 11, and then my largest negative value is -5. And so I'll make my graph here, and I'm going to use the same graph. I'm going to do each one of these in a different color, and I think that will be a good way, a clever way to do this all on the same page here. So I don't have to draw 4 different graphs. But you're going to have to draw some different graphs, or at least put them on the same picture like I do here. So let's say that's going to give me room there to do that. Yep. So this is going to be 1, 2, 3, 4, 5. I don't want to go more negative than that. I did not lift my pen. Did not do it. Didn't lift my pen. There's that. Okay. And we're not going to go more than -5, so I'll go like that. I'll need a horizontal line though. Okay, so I think this should be enough room for me. Then I'll do this first one in, why don't I go with blue for this first one. So number 19 I'm going to do in blue, and see what I got here. So what kind of special type of quadrilateral is PQRS? So I'm going to connect the dots here. 0, 3. 0, 3 is going to be this point right here. So I'm going to start here, and then I'm going to go out to 5, 6. So I go out 5, and then I go up 1, 2, 3, 4, 5, 6. I've got another point right there. 2, 11. I'd be going out 2 this way, and then up 11. I'm already at 6 right here, so 7, 8, 9, 10, 11. I got another point right there. And then -3, 8. So I'm going to go, this is 11, 10, 9, 8, and I would put -3, 8 right there. So if I connected all those, it's saying what kind of quadrilateral is that? And I think just to make this a little easier, I'm going to draw in at least every 5. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It'd be 10 right there. This would be -5 down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 right there. So looks like we're, that is not a good looking 0. It's a little better. Right, so that's the first one. Why don't I draw all the pictures in first? So I'll do number 20, I'll do in red. 0, 0 right here. 6, 8. Here's 6. Going up to 8 right there. 2, 11. Nope. Looking at the wrong one. 8, 5. 8, 5. We're going to go 7, 8. And 5 will be right there. And then 4, negative 6. 4. It's going to be down there. Negative 6. I missed that one, but I got enough room so I can squeeze it in. That'd be like right there. 4, negative 6 right there. Come on, there we go. And reconnect that. Okay, so what kind of quadrilateral is that one? I'll do this next one in green. So 21 I'll do in green. That'd be 2, negative 1. 4, negative 5. 0, 3. Negative 3, sorry, 0, negative 3, and negative 2, 1. So negative 2 and 1 up here. That one looks like it might be a parallelogram. This one looks like it might be a trapezoid. This one might be parallel to that. Same here and here. It might be a trapezoid. I'm not sure totally yet. This last one I will do in purple. 22, I'm going to have negative 5, 0. There's a point right there. Negative 3, 6 right there. 1, 6 is going to be a point right here. And 1, 2 is going to be 1, 2 right there. I'm going to have a point. That one might be a kite. Not totally sure about that. It almost looks like kite, but I can't be positive about that. So let's go back to blue. And let's check out number 21. Let's see what we think about, or number 19, sorry. Let's see what we think about that one. And I just noticed something about this one. I went up too far. So that was supposed to be 1, 6, not 1, 7. So let me redraw that one. Oh. There we go. Put that one back in there. So negative 5, 0, negative 3, 2, 3, 6 right here, and then 1, 6 should be right there. 1, 2 should be right there. Okay, that looks better. But again, let's go back to number 19 and see what we think about that one. I am not having a good time here. I think I've made too many videos in a row. That's my excuse, I think, for this. But that is not drawn right. I think these points were all good. This was 5, 6. Yeah, this is 2, 11. Did you catch my mistake though here? Negative 3, 8, 0, 3. This is 3, 0. This point should be moved up to here. And I don't think I can easily drag that here because it's all one shape. So let me redraw the blue one. And then I might need to redraw some of these other ones. I'm not sure there. Okay. And yep. So let's draw the blue one. 0, 3, let's try this again. Boom, right here. No, not quite there. Blue, 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 blue. 0, 3, right there. Negative 3, 6, not the one I'm looking at. 5, 6, right there. Agreed, yes, okay. 5, 6, 2, 11, right there. And negative 3, 8. Negative 3, 8, there's 10, so 9, 8, negative 3, 8, yes, right there. Connect it. Now that's looking more like what I thought it might be. Alright, so to me, number 19, this blue one, looks like it might be a square. How could we check that though? How could we make sure? We would both have to check that the sides are going to be all congruent to one another. And if we checked if they were 90 degrees, we could check if the slopes are opposite reciprocals. I'm going to do this one a little different than what the book has here because that's a possible way. You could also check the lengths of the diagonals and see if they bisect one another. That's the way the book does it. That would prove it's a rectangle. But if you prove it's a rectangle and a rhombus, then you're good. So I'm going to prove that it's a rhombus first. If you prove it's a rectangle and a rhombus, that means it has to be a square. So I'm going to prove that this is the same length as this by looking at these points up here. So If I can prove all these things are the same, then we're going to be good to go. Alright, so the length of each one of these, you could use the Pythagorean theorem, you could use the distance formula as well, but it doesn't show up very well if I had the orange here right there. So I'm going to notice that each one of these orange triangles that I'm drawing, they're all right triangles, and they all have, this is their hypotenuse, the blue length. And if they're all the same, then I can just show you what one length is and say that's going to be the same for all of them. So I can say this is 3, and I can see that this is 1, 2, 3, this is 1, 2, 3, 4, 5. And so the length of this one, if I just use that idea, I can prove that this is all 3 and 5, 3 and 5, 3 and 5. So I see that those are all the same. So this one I'm just going to say 3 squared plus 5 squared would equal c squared, your hypotenuse. I'll call this c. So c squared would be 9 plus 25 is c squared. I mean, c squared would be 34, and so c would equal the square root of 34. This is the same thing because these are all the same. This is the same thing as PQ. If I were to label each one of these, I'm not going to label all here. There's just going to be too much writing there if I do all that. But I'm going to get rid of the orange stuff now. So you saw all those orange triangles were the same. They were both, or they all had lengths of 3 and 5 for the legs. And so that means that these are all the same all the way around. These are all going to be C, 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 and C. And so this would be the length of PQ. Here's P. I'll write these in and get rid of them later. So this is P, and this is Q right here. This is R, and this is S over here. So each one of these had this length. PQ, that would equal QR, that would equal RS, that would also equal SP. And so that implies that it's a rhombus. And then if I find the slopes of each one of these, each one, yeah. So if I find the slope of PQ, the slope of this is going to be up 3, right 5. So the slope of PQ, segment PQ, is 3/5. The slope of RQ is negative 5 over 3. The slope of SR, or RS, is also going to be 3 over 5. So this is a slope of RS as well. The slope of QR, though, was, so I'm going left to right, going down 5, right 3. That's a minus 5 over 3. That's going to be the same thing as the slope of SP, minus 5 over 3. And so based on these things, that implies that they're opposite reciprocals, 3/5, negative 5/3. The slopes are opposite reciprocals. So that means we could say that this here is perpendicular, this is perpendicular, this is perpendicular, and this is perpendicular. That means it's a rectangle. So slopes are opposite reciprocals. So they're perpendicular, which implies it's a rectangle. And since it's both a rhombus and a rectangle, that implies that it is a square. Okay, so lots to talk about there with that one, but we proved that opposite sides, or all sides, were congruent. That means it's a rhombus. We proved that all these sides were perpendicular in the way you see here in the picture. That proves it's a rectangle. That means since it's a rhombus and a rectangle, that it is a square. So I'm going to get rid of, I didn't want to get rid of the 10, but I wanted to get rid of all that stuff there. I'll put the 10 back. And now I'll do 20. So 20, I'll see if I can put that up here. So 20. Looking at that, looking at this picture, to me that looks like it's going to be a little shorter than that. I think that's pretty clear just looking at it, but it looks like this might be true. It looks like this one might be parallel to this one. So I'll I'll say that with a question mark beside it. And I'm going to check that out. So P is right here, 0, 0. This is 6, 8 right here, that's Q. R is at 8, 5, S is down here. And let's see what we got. So I think that QR might be parallel to PS. And so if I go down here and check my slope, I'm going to go down 6 and then right, that is 4. So the slope of PS equals, that is down 6 minus 6 over 4. That's the same thing as negative 2/3. If QR is the same, do I go down 3 and right, I'm sorry, down 3 and right 2 that? Yes, I do. That should have been negative 3/2, not negative 2/3. So the slope of QR is the same thing as this one was reduced. So these are the same. That means, yes, I can get rid of that question mark. This is, in fact, parallel to this one right here. These two doesn't look like anything special about them, so I'm not going to check anything there. These ones, if you checked their slopes, you would actually get, this would be, what would that be, 8 over 6, which would be 4/3. And then this one would be going down from negative 6 up to 5. That'd be 11 over, going from 4 to 8, 11 over 4. So the slopes of those are not going to be the same. This one I'll just say slope PQ does not equal the slope of SR. And so this being true, this implies that you have a trapezoid for that. So that's the property of trapezoids that we need to remember, that you have one pair of parallel sides. Okay, let's look at the green one now. Let's look at 21. So this one, 21, green, there we go. This one looks like it could be a parallelogram. It even looks like it could be a rhombus. And so let's see if I can draw the same triangles that I did like before. If I can draw all the same looking triangles, then I can say that, hey, you know what, by the Pythagorean theorem, those are all going to be the same lengths. So this one is a difference of 4. 1, 2, 3, 4. This is a difference of 2. Can I draw the same triangle? Can I draw triangles with legs of 2 and 4 everywhere? This one's 2 and 4. This one is, yep, 2 and 4. And this one is also 2 and 4. And so based on that, I can do the same sort of thing I did here. I can say that 2 squared plus 4 squared equals, all of these would be the same. All of these would be C. Honestly, I feel like that's enough. Like, you showed that the right triangles off of each part, each side of the potential rhombus, they all have to be the same. They're all the same triangles. That means they all are going to be the same after you solve this. But let's just do the math on this. 4 plus 16 is 20. And so C would be the square root of 20, which would be the same thing as 4 times 5, which would be the same thing as 2 radical 5. You can take out the 4. Square root of 4 is 2. And so they all have this length, PQ, QR, RS, and SP. If you were to label these things like we did before, that's what you'd have. That implies that you have a rhombus on this one. This one, they're not going to be squares because, well, that's clearly not going to be a right angle right there. I hope that's pretty obvious just looking at that. So a rhombus, yes. A square, not on this one. Alright, and I don't think, yeah, I don't need that anymore. I can erase that too. So the purple one looks like a kite to me. We got to prove it's actually a kite though. So 22. I'll work this one out over here. So if it's going to be a kite, this would have to be congruent to this, and this one would have to be congruent to this one. So let's see if that's actually the case. This one's easy to count. 1, 2, 3, 4. And right here, 1. Why does that look so crazy? I don't know. 1, 2, 3, 4. they're both 4. So this one, P is right there, Q is -3, 6, that's right here, R is here. What is going on with purple? It doesn't like that. I don't like how that looks at all. It's like bleeding, it looks like. I don't know. That's P, Q, R, and S. Maybe I can't use purple. Anyway, QR. It's going to be the same thing as RS, which is going to be 4. We counted that jump. Let's go back to a color that doesn't look so crazy. Okay, this one and this one. They're all doing that now. What is going on? What is going on? My computer's getting tired. I don't know. 2. This is 1, 2, 3, 4, 5, 6. Is that the same thing over here? What the heck? I think my battery's going low. No. I need to finish this. This is 6. This is 2. My battery is going low. Yes. And so each one of those, you've got this 2 and 6. This would be a C and a C. So we've got 2 squared plus 6 squared equals, oh boy, equals C squared. Stay with me, man. You can make it. You can do this. Do I have the charger? I don't even know if I have the charger here. This would be 36. The C squared. This would be 40. I might just have to use the laptop itself. Let's try this. I haven't done this before, but this is rough too. Equals C squared. Okay. So you take the square root of both sides. Ugh. And you get I'm using the touchpad on my laptop now, and this does not work as well. You get that, which is the same thing as the square root of 4 times 10, which is the same thing as this can come out as a 2. So you have 2 radical 10. And so we could say, let me see if I do have the charger. And I do have the charger. So let's see. Yes. Okay, this is a 2. And so this is going to be the same thing. 2 radical 10 will be this one right here. That was PQ. And it'll be this one as well, PS or SP. This both equal each other. That implies that since these two are the same, and since these two are the same, I'm going to bring this down here. Woo, I'm saying this all goes together. This together with this implies that it's a kite, because consecutive sides, you have 2 pairs of congruent consecutive sides. So some pretty involved problems there. Some bleeding looking colors there too, but that was pretty weird. Anyway, let's move on to the last set of problems. Area. Okay, this is pretty straightforward. This should be pretty nice way to finish up here. So area, nice to see it. Area. Find the area of the triangle or quadrilateral. So what is the area of a triangle? Area of any triangle is 1/2 base times height. There's those formulas, you just have to memorize those. You just got to get those memorized down pats. 1/2, the base here is this part, and then the height is this part. It's the part that's perpendicular to the base. Even if it doesn't touch the base, it's still perpendicular to it. It's still the straight up and down height with respect to this base. So the base is 1.5 or 8.5. It's 1/2 times 8.5 times the height is 7. And so this becomes 1/2 times 8.5 times 7. This would be 7/2. You can do multiplication in any order. This one I'm going to get out my calculator for, though, because we got a bunch of halves multiplied together. So I could say 1/2, that's the same as 0.5 times 8.5 times 7. That would be 29.75. And this one gives me units. It gives me inches, so I need to include those units. Inches, it's inches times inches. This is this many inches times this many inches. That's inches squared. So that should be the answer for that one. And that's the same thing. The book gives 29 3/4. That's the same thing. So you could give either one of these answers. Number 24. With this, it is a trapezoid. So this one, because this is perpendicular to this, that means one of our old theorems way back a couple chapters ago said that perpendicular parts here, that means these lines have to be parallel. So if they're perpendicular to the same line, they're parallel to each other. And so this is a trapezoid because of that. And for the trapezoid, the area of the trapezoid was 1/2 of, or it's, in other words, the average of the bases times the height. So we can do the average of the bases times the height. If you write the height in front here, that's okay too, but it's the half. I like to write it like this sometimes because that just reminds me it's the average of the bases times the height. So I have 1/2 of 3 plus 6 times the height is 3. So these are my two bases, and this one is my height. It doesn't really matter if you call this B1 and this B2 or vice versa, but just know that these are the two bases. So this would be 1/2 of 9 times 3. Looks like we'll have another fraction on this one. If you wanted to write them all as fractions, you could, and then multiply all the tops together, you'd get 27. All the bottoms would be 2. Excuse me. 27 halves is the same thing as 13 and 1/2. And this is going to be its feet, so feet squared for an area. So you could say this, or you could say 13.5 if you used a decimal, 13.5 feet squared. And then finally we have a kite. It looks like we've got this congruent to this congruent to this. That formula for a kite, the area of a kite, was still used 1/2 because we have, it's like half of this rectangle if you were to draw the rectangle on the outside of it. So it's half of that, and this would be one of the diagonals, the other one would be this diagonal. So from here to here we have 6. It's 3 plus 3 right here and here. So it's half of the area of the rectangle formed by a 6x4 rectangle, because each one of these are triangles that take up half the space right here, half the space right here, here, and here. So area of a kite, it's 1/2 times the diagonals. It's 1/2 in this case times 6 times 4. Half of 6 is 3. 3 times 4 is 12. No units given on this one, so you can just leave that off. If you wanted to write something, if you were desperate to write something, you would write units, the actual word units, squared. You could also write square units. The book gives you this is the same thing. SQ units, square units is the same thing as units squared. Okay, so we had a little bit of trouble with this one where the pen started quote unquote bleeding. We had this one where I gave you a longer way to prove it than what the book has. Check out the book for the easier way to do that. And I think the rest of them were, oh yeah, this one too. Yeah, not my best day here. The book, I think though, is to blame on this one. The book has the wrong answer for this, and so I disagree with the book on this one. It could be an isosceles trapezoid. But beyond that, I think the rest are pretty straightforward. Yep. So that'll do it. Hopefully that helps, and hopefully you do well on your Chapter 6 test.